There it goes. Okay. We're going to look for the radius and interval of convergence of this infinite series right here. Okay? Now, to start this problem, the first thing to do is let's go ahead and do the ratio test. Okay? So, you say the limit as n tends towards infinity, okay, and this is going to be the absolute value of 2x minus 1 to the n plus 1 divided by the square root of n plus 2, and then this thing would be the square root of n plus 1 and divided by 2x minus 1 raised to the nth power. Let's close those absolute value signs. Okay. And I would manipulate the problem in this way. The limit as n tends towards infinity. The absolute value of 2x minus 1. We can put both of those under a square root sign. N plus 1 divided by n plus 2. And then I could say, all right, let's divide by the highest power inside of the square root. And so that would equal the limit as n tends towards infinity of the absolute value of 2x minus 1 and everybody under the square root. That's 1 plus 1 divided by n divided by 1 plus 2 divided by n, like that. All right, now the root test says that this always has to be less than 1, okay? So this will equal 2x minus 1, which has to be less than 1. Okay. But 1 is not the radius of the problem, okay? So, I'm going to take that absolute value of 2x minus 1, which is less than 1, and we're going to divide everybody by 2, divide by 2. And I end up with x minus 1 divided by 2 is less than 1 divided by 2. And that right there, that is our radius, 1/2. Okay? So, this would give us that negative 1/2 is less than x minus 1/2, which is less than 1/2. And then if I add 1/2 to everybody, we end up with 0 is less than x, which is less than 1. Okay. Now, we've got our radius of convergence of this problem. What we have to do at this point, so by doing the ratio test, we determined that this thing is convergent between 0 and 1, and it's absolutely convergent. Outside of 0 and 1, this thing is going to be divergent. We don't know about 0 and 1. So to get the true interval of convergence, we're going to have to check x which equals 0 and x which equals 1. So start with the bigger one. Okay, so we're going to check x which equals 1. And so this would turn into the sum n equals 1 to infinity of 2 times 1 minus 1 raised to the nth power divided by the square root of n plus 1, which would equal the sum n equals 1 to infinity of 1 divided by the square root of n plus 1. Okay, now that we got to this point of the problem, you can do this in a couple different ways. But I would say the easiest way to do it is probably the limit comparison test. Well, a direct comparison test would also work. Would it work? Oh no, you'd have to get in some type of weird convoluted argument. Anyway, let's do a limit comparison test. All right, and so I'm going to do a limit comparison test. The limit is n tends towards infinity of 1 divided by the square root of n plus 1, and I'm going to compare it with the p-series of 1 divided by the square root of n, okay? And that would equal the limit as n tends towards infinity. Another way, that would be, let's put them all under square roots. N over n plus 1, all right? Then I could say, divide by n on the inside of the square root. Which would equal the limit as n tends towards infinity of the square root. Now this would become 1 divided by 1 plus 1 over n. Okay? As n tends towards infinity, that will tend towards 0. This will tend towards 1, which is greater than 0. Right now, since the sum n which equals 1 to infinity of 1 divided by the square root of n is divergent, x equals 1 is divergent. By limit comparison test, but we already cited the limit comparison test at the beginning. Okay. So we know that one endpoint is divergent. Now we got to check that other endpoint. So now I'm going to check x which equals 0, and so that will turn into the sum n equals 1 to infinity of, this would be 2 times 0 minus 1 raised to the nth power divided by the square root of n plus 1, which would equal the sum n equals 1 to infinity of negative 1 to the n divided by the square root of n plus 1. Okay. All right, so what we're going to do on this case, use the alternating series test. Okay. So for the alternating series test, we have that 1 divided by the square root of n plus 2 is less than 1 divided by the square root of n plus 1, and the limit as n tends towards infinity of 1 divided by the square root of n plus 1 does equal 0. Okay? So, x which equals 0 is convergent. Hence the interval of convergence is 0 less than or equal to x, which has to be less than 1. That is the interval of convergence of that problem.